Hello, I'm Alberto Soto with Siemens PLM Software. Today, I'm going to present how to run an analysis of the startup of an air cycle machine integrated in an aircraft environmental control system. In particular, I will demonstrate how Simcenter Amesim enables you to quickly assess system performance under different operating conditions. To do so, I will first summarize how an air cycle machine works. Here, you can see a typical schematic of a four-wheel air cycle machine. The compressor, two turbines, and a fan are mounted on the same shaft. Hot air, bled from the engine compressors, passes through the primary heat exchanger, where it is cooled before entering the compressor. Compressed air passes through the main heat exchanger, a reheater, and a condenser before entering the first turbine. At the exit, air humidity is removed by another passage through the condenser, before entering in the second turbine. At this point, the cooled air is conveyed to the mixing unit. Now, let's have a look at the software. Here, you can see the corresponding Simcenter Amesim model built using the gas mixture and the moist air libraries. You can notice how Simcenter Amesim's iconography allows the immediate recognition of each system component. For example, you can see how the compressor, the fan, and the two turbines are mounted on the same mechanical shaft. By zooming out, it is possible to appreciate the whole model which, at this stage of design, is assumed to be symmetrical. Each pack inlet is connected to the respective engine bleed port, while the outlet is connected to the mixing unit. A trim air valve is used to regulate the flow rate of the hot bled air to increase the temperature in the mixing unit if needed. The associated control is based on the cabin temperature and controls the opening of the ram air channel valve. Boundary conditions, representing the atmosphere, are based on standard models, like the International Standard Atmosphere, which is implemented in Simcenter Amesim. These conditions vary depending on the aircraft speed and altitude. The integration of the air cycle machines with the rest of the environmental control systems enables the implementation of control strategies that ensure optimal passenger comfort. Let us now conclude this demonstration by looking at the simulated scenario and results. The aircraft is resting on the ground at the start of the simulation. After 2 seconds, as seen in the first soft plot, the engine 1's flow control valve is opened, letting hot, pressurized air flow through the air cycle machine. As the flow control valve is opened, pressure will build up, accelerating the turbine. This is reflected on the shaft speed showed in the third plot. Now let's have a look at the temperature regulation. In this plot, you can see the temperature target in black and the actual system response in blue. The opening fraction of the trim air valve is shown in red. We see that it takes a few seconds before the environmental control system's pack becomes operative and able to regulate the temperature. Also, the trim air valve is controlled effectively, reaching an optimal temperature for passenger comfort. To sum up, Simcenter Amesim helps you study environmental control system performance in an effective way, especially in response to varying boundary conditions at different stages of the design cycle. Thank you for watching. For more information, please visit our website.